Hello, my name is Nitin. Until now, compliance testing of Wi-Fi 6E with DASY 8 or 6 has been cumbersome as the compliance distance of 2 millimeters is much smaller than one-fifth of the wavelength. One-fifth of the wavelength was the shortest distance that the plane-to-plane phase reconstruction of DASY 8 module millimeter wave version 2.0 was accurate for. As probably all of us noticed, the workaround offered by SPEAG was not really satisfactory. As previously announced, SPEAG teamed up with its R&D partners Zurich MedTech and the ETIS Foundation and developed two completely new solutions, namely for incident power density and the absorbed power density. In this video, I will now test if this new module millimeter wave 3.0 has solved the problems of the previous versions. In particular, the limitation with respect to the closest distance and the restriction to planar surfaces. The new feature of DASY 8 module millimeter wave version 3.0 is based on latest research results on the equivalent source reconstruction algorithm. The new method is based on a novel multipole source reconstruction algorithm and has recently been submitted for publication. In the manuscript, of which I have received a copy, it is demonstrated and validated that the algorithm is accurate for very small distances in terms of wavelength and allows to evaluate, for example, surfaces on top of which the camera module is evaluated. The new method also allows to assess the exposure inside concave surfaces such as in the goggles. Today in this video, I will evaluate version 3.0 by running measurements on this special patch antenna at 5.7 GHz that we have received from a customer as benchmark. I already have simulation results for this antenna and we will see how good the new algorithm performs with respect to the simulation targets. So here I have the antenna set up on the millimeter wave phantom. The antenna is fed with a signal generator and the input power is monitored via the two power sensors connected to a bidirectional coupler. The project setup in DASY 8 or 6 module millimeter wave 3.0 consists of a fast area and 5G scan at 2 mm from the surface. The equivalent sources algorithm is enabled from the preferences. The other settings are left to default values. I start the measurements and accelerate the video. The fast area and 5G scan measurement grids with this algorithm are similar to the previous versions, i.e., the scan times are the same and do not increase if the new algorithm is used. So the scan is now finished and the equivalent sources reconstructed. The total peak spatial power density value is 961 and 645 watt per meter square, corresponding to 1 and 4 centimeter square averaging area. This is only 0.6 dB from the simulation values. The new algorithm definitely performs better and provides much lower uncertainty for the bands below 24 GHz, where the evaluation distances are less than lambda by 5. However, this is not all. The most exciting new feature is that by computing equivalent sources out of my DASY measurements, the millimeter wave module allows me to have effectively a full digital model of how the device under test radiates under the tested conditions. And this digital model is portable. All the information is encapsulated in a single file. I can easily export it out of DASY and import it into my Sim4Life simulation software for more analysis. Here is how it looks like. When I import the file created by DASY into Sim4Life, I can easily see the geometry of my DUT and some identifiers so that I can always trace the file back to the physical device. The important thing is that this will make validation of the numerical model obsolete. For example, I can place my DUT in different virtual scenarios next to a hand phantom, next to a full body phantom, oh boy, next to a high resolution anatomical model such as Duke. Within a few seconds of post-processing time, I can easily propagate the radiated fields in free space and compute, for example, the incident power density in those scenarios. It is very flexible and powerful, and I like how I can actually use the data that I have just measured. What I cannot easily do, it seems, is use these fields as excitation sources for the different electromagnetic solvers. For example, to simulate the absorbed power density or the specific absorption rate. I am sure SPEAG is already working on making that feature more accessible. The new field reconstruction algorithm in the mmWave module addresses important issues such as evaluations closer than 1/5 of the wavelength, measurements on non-planar surfaces and concave surfaces, replacing simulation models with measurement-based models. It is great to see that SPEAG continues to leverage its expertise in both hardware and software solutions for mmWave compliance testing. Being able to use measured data into my simulation software offers a whole new range of possibilities, either for increasing the confidence in results or for exploring scenarios that are out of reach of measurements or simulations alone. This is already a huge step, and I am excited to see what comes next. In my next video, I will demonstrate how to measure the absorbed power density of this antenna. More information is available at www.speag.swiss about the latest DASY 8 or 6 module mmWave 3.0 and from www.zmt.swiss about the just released version Sim4Life 7.0. Thanks for watching this video.